The Spectrogram Classification Part 1. In this tutorial, I will explain what spectrogram is, how a normal sleep spectrogram looks like, and how sleep abnormalities present themselves in spectrograms. Section 1. The spectrogram. The top panel of the figure shows an example of a 30 seconds long EEG recorded during wakefulness. The lower panel shows the respective multitaper spectrogram. The x-axis of the spectrogram shows the time, just like the EEG, but unlike the EEG, the y-axis shows the frequency. The color coding, given decibels, represents the activity in a given frequency range. In this example, strong activity around 8 Hz can be observed throughout the recording. This dominant 8 Hz frequency typically indicates wakefulness. Furthermore, intermittent eye blinking during wakefulness can be observed around 0.5 Hz. Generally, the spectrogram is a way of dynamically visualizing the spectral content of a complex signal over time. Section 2. How normal sleep should look like. Normal sleep occurs in cycles. The sleep cycle starts by a transitioning of wakefulness into a phase of light sleep, also known as N1 sleep stage. The N1 stage is of short duration, normally followed by a longer-lasting stage of light sleep, also known as N2 sleep stage. In healthy individuals, light sleep is followed by deep sleep, which is known as the N3 sleep stage. At the end of a deep sleep phase, individuals usually transition into REM sleep, which is characterized by rapid eye movement. The end of REM sleep completes a full sleep cycle, which may repeat 3 to 5 times during a full night of sleep before getting up again. This figure shows an example of a normal sleep hypnogram, a graphical representation of the different sleep stages during the night, being REM highlighted in green. Below, we observe now the spectrogram. Without knowing much about the spectrogram, we can already observe repeating motifs throughout the night that correspond with wake, non-REM, and REM. Among different patients, they present heterogeneity in the spectrograms. Nevertheless, they share similar patterns for each of the respective sleep stages. It's common for individuals to experience awakenings during their sleep, and this is normal. As you can see on the hypnogram, we have these occasional awakenings represented as short interruptions in the sleep cycle. These are not necessarily something to worry about, as long as they are short-lived and you can quickly return to sleep. We can observe also these awakenings in the spectrogram. Remember, what truly matters is the ease with which you can return to restorative sleep after an awakening. Let's focus on one of the essential phases of a normal night's sleep. The REM stage. Understanding what a normal REM phase looks like is crucial for assessing the spectrogram. You'll see REM sleep typically occurring in cycles through the night, and each cycle becomes longer as the night progresses. A full night's sleep often consists of multiple REM phases. On the other hand, deep sleep, or N3 stage, typically occurs earlier in the night and becomes less prominent as the sleep cycles progress. Deep sleep is characterized by slow brainwave activity. This is why we observe it in low frequencies in the spectrogram. Up to this point, we've delved into the characteristics of typical sleep patterns. Now, let's summarize the essential takeaways. These include the occurrence of sleep cycles, brief awakenings and quick return to sleep, and the significance of having REM and deep sleep throughout the night. By examining the spectrogram, we can extract information regarding the patient's sleep stages throughout the entire night, thus providing insight into the patient's normal sleep. Section 3. Examples of normal and abnormal sleep spectrograms. As a preliminary exercise for the experiment, we are going to observe only the spectrograms and the respective key points for normal sleep that we have just discussed. Here's an instance of a normal sleep spectrogram. In this case, we can observe distinct sleep cycles which repeat up to 4 times. Additionally, we can identify brief awakenings with swift recovery. Furthermore, both REM and deep sleep stages are discernible throughout the night. Therefore, we can conclude that this example exhibits characteristics consistent with a normal sleep spectrogram. On the flip side, here is an illustration of an aberrant sleep spectrogram. Let's dissect the key aspects to see why. Initially, this patient doesn't adhere to the typical sleep cycles, as we can only discern a solitary sleep cycle. Furthermore, we can pinpoint instances of nighttime awakenings, including some brief ones and one of extended duration. However, this long awakening does not directly signify that the spectrogram is abnormal, but it does serve as an indicator that something unusual may be occurring. In conclusion, this example deviates from normal sleep patterns due to its failure to complete sleep cycles throughout the night and the occurrence of only one REM stage. Thank you for watching. You may continue with spectrogram classification Part 2